There's a huge number of materials that can be used in different kinds of design. They serve different functions because they have different properties. The properties of all materials at a large scale are based on their small scale structure, the structure of their molecules, their crystals, the way the atoms are arranged. That is what ultimately determines every property that exists at a large scale. Wood has this complex molecular structure. It has long chains of carbon, it has long fibers, and it has soft structures. And so it makes this composite that has a particular set of properties. And each type of wood, in fact, has different properties from each other type of wood. Through covalent bonding, we've talked about how there are two main types of bonding that you learn in chemistry, covalent and ionic. Those are not the only types of bonding, but those are what we focus on most often at this level. Covalent bonding can join smaller molecules into these long chains called polymers. So the smaller molecules are called monomers. When you put a bunch of monomers together, you get a long chain called a polymer. Proteins are polymers of amino acids. They can form long strings that fold themselves into specific shapes, and they can transfer tension. A very large molecule is sometimes called a macromolecule. You've probably learned about macromolecules in biology and then reviewed them again, possibly in chemistry. They're often modeled using smooth shapes instead of showing all of the individual atoms. It would be difficult to see the overall structure of a protein if you drew each atom that makes up the protein. So often we just draw the general shape. The Think of a metal. Okay, metallic bonds are something you might not have covered much in chemistry. In a metal, you have a bunch of ions, metal ions. That's the nuclei and some of the inner electrons surrounded by and sharing a sea of electrons. So the outer electrons of the metal ions can move freely throughout the structure. And since they can flow anywhere in the metal, that leads to some of the macroscopic properties of metals. The fact that they can conduct electricity, for example, the fact that they can conduct heat. Covalent bonds can form in specific directions. For example, carbon atoms will have bonds in 4 directions. They'll form tetrahedrons, these kind of pyramidal structures. They form crystals like diamonds and graphite. Graphite is what we often refer to as pencil lead. So uh, it's a very soft structure compared to a diamond. So how might stress affect those types of crystals? Covalent crystals, they might stand up to compression in the direction of the bonds, but they might not stand up so well in other ways. They might bend or deform in other ways. The bonds might spring back or they might break, especially under great enough shear stress. So the direction of the bonds, the structures that are formed, help determine what kind of stress the crystals can withstand. Here we have a bar of gallium. Gallium is interesting. You don't want it to touch your bare skin, but it is a solid at room temperature, but at slightly above room temperature, it turns into a liquid. So if you hold it in your hand, it will change to a liquid. So what's going on in there? What are the forces that exist between the atoms that change it from a solid to a liquid? And this is something that you covered more in chemistry or will cover more in chemistry. But the strength of the forces between the molecules affect whether an object is solid, liquid, or gas. In a solid, you have stronger forces or actually, in a solid, the forces between the atoms or molecules actually hold it in a rigid structure. In a liquid, the forces are still significant, but they are but the movement of the particles enables them to move relative to each other, so they can flow past each other. In a gas, the forces between the particles are not significant. Each particle is able to move around freely. So let's complete this sentence. The molecules or atoms of a gas are farther apart than in a liquid, or so the electrostatic forces between them are weaker because remember, electrostatic forces become weaker when the distance increases. In a gas, the main interactions between particles are collisions. So those attractive forces are not significant. Those electrostatic forces are not significant. The main interactions between the particles are collisions. As the particles collide with the container walls, they exert pressure. Gases, like liquids, deform easily under tension and shear stress. They respond to compression by changing volume, getting smaller. Or not, the particles don't get smaller, the particles get closer together, and so the gas reduces in volume. And they exert more pressure when they're pushed closer together. They exert more pressure on the container walls. Because the forces between particles are weaker, gases expand to fill a container. When they're compressed, like if you take a bunch of air from a room and pack it into a scuba tank, they exert increased pressure on the walls of the container, and the frequency of collisions between the gas and the container increases. When a fluid is compressed, the fluid presses on all sides of the container. And so engineers use this phenomenon. They put fluids into cylinders or tubes, and they can use that fact that the fluid presses on all sides to transfer force from one end to another. There are two types of technology: hydraulics and pneumatics. Hydraulics are liquid-based, pneumatics are gas-based. And both of these involve compressing a fluid. Fluid is a liquid or a gas or anything that can flow. So in hydraulics or pneumatics, the fluid is compressed, and that can transfer a force because you compress the fluid in one part of the system and it pushes out on every other part of the system. So you can transfer the force to a different location and in a different direction. In this case of a pneumatic dog, pneumatics, there's an air compressor that compresses air into a tank, and then you have compressed air. So the compressed air is released through these red tubes of gas to move the robot's limbs. So when a valve opens to release air through one of these tubes, the air transfers into a cylinder at the dog's legs, for example, and that causes, we can see those cylinders in black, and those black cylinders, when the air expands inside them, a piston moves out and it causes the leg to extend or compress depending on in which direction the air is flowing. Whoops, I left the answers up. They're gone now, but we're going to get to them in a moment anyway. Here we have a macro, or here we have a very close-up view of some substance. And we know that the macroscopic properties of the material are determined by its microscopic properties. So here's a microscopic view. What can we see here that might help us determine the macroscopic properties? Well, we can look at atomic level or molecular level interactions within a material. That's something that's really hard to see. You would need it's almost impossible. We can't see that here, but we can see larger structures within the material, which are in turn a result of the atomic level and molecular level interactions. So let's look at this image. This is an image taken by an electron microscope, so it's a very, very zoomed in image. We can say that the open spaces suggest that it can be compressed easily, right? Because if you can push the solid parts together, then it can be compressed. So this is an object that can probably be compressed easily. It's likely to be of low density because it has a lot of open space within it. And it seems to be made of fibers, and it probably has covalent bonds in those fibers. This material is most likely in a paper towel. There were some options in your Explore Explain, and the most reasonable one is paper towel. The open spaces and irregular structure suggest fibers and a compressible structure of low density. Recall that covalent bonds can lead to long molecular chains that hold up well to tension. The table describes common reactions of various materials to the application of different stresses. Let's match the corresponding descriptions of a material to the reactions to stresses. And we're going to classify each material as elastic or plastic where indicated. So first we see we apply compression stress and there's little or no change. That is a hard material. Hard materials are difficult to deform. If there's tension or shear stress and it breaks, then that's a brittle material. Remember, brittle materials don't bend, they break. They don't bend much, they break. If it compresses, stretches, and bends, it is tough. Okay, tough materials, they do deform, but they tend to return to their original form, while malleable materials stay deformed. If the object returns to its original form after being compressed, if it was a hard object that returns to its original form, then we call that elastic. If it was a tough material that returns to its original form, we refer to that as elastic. And a malleable material that where part or all of the change remains, that is a plastic deformation. It might seem weird to think of a metal as plastic or a hard substance as elastic, but to an engineer, these terms describe the behavior rather than the substance. Here we see a few methods of joining materials. We see some screws holding boards together. We see some poles that are lashed together, and we see a bird's nest stuck to a wall, or I assume a wall, or maybe it's inside a birdhouse. I'm not sure. But if we choose two methods of joining materials, well, actually, let's look at this first. When two materials are very close or in contact, their surfaces may experience attractive or repulsive electrical forces. Repulsion between the electrons in two surfaces produces a normal force. Remember, normal force is when two objects are in contact, but when they're in contact, what that really means is that you have repulsive force between the electrons of one object and the electrons of another object. Attractive forces may cause materials to stick together. Like we've seen that with balloons and Scotch tape and other objects that we've charged. These images show ways of joining materials. So here we see some boards screwed together. We see some poles lashed together. We see the birds stuck to the wall, or the bird's nest stuck to the wall, and the birds sitting in the nest. For each one, which types of stress are involved and which forces are at work? Well, with the screws and lashing, we see compression of the parts. We see the boards compressed together. We see the poles compressed together, and we see tension in the fastener. Both the screws and the rope are in tension. That's what's those competing forces of tension and compression are what holds those objects together. The bird's nest is stuck onto the wall by some kind of adhesive that works against shear stress. That's why it doesn't fall off the wall. At the atomic and molecular level, there are electrostatic forces holding parts of the material together or attracting and repelling surfaces of different materials. In this image, we see a gecko climbing up glass. How can an animal that it's not super heavy, but it does have some weight to it. How can a gecko like this cling to a smooth or a seemingly smooth surface? We've already seen how we can comb our hair and then with a plastic comb and then wave the comb over little bits of paper like confetti, and the paper will be attracted to the comb. the gecko clings to glass in a similar way, using electrostatic attraction, which is really fascinating if you think about it, about how an animal can cause electrostatic forces um, to be exerted by its feet. And the way it does that is by using carbon-based molecules on its toes that can actually become polarized. And remember, polarization is where one end of an, an object becomes um, partially charged, while the other object has the corresponding charge. So one end is positively charged, the other end is negatively charged. So what's happening here, where we have a window washer that is climbing up or climbing across a building? Now, obviously, he has all kinds of safety ropes there. He's not as self-assured as a gecko climbing a wall, but is this the same thing? Is it electrostatic attraction that's holding him up? The answer is no. Okay, so what happens is he has these suction cups, and if we think about tension, compression, shear stress, and we think about what's happening at the molecular scale, what's happening is that those suction cups, there's really no suction force. Okay, it's not a thing. What there really is there's a pressure force, an air pressure force. And so when the air is removed from underneath those suction cups, the air from outside the suction cups pushes on the surface and pushes them against the building. And so this window washer is able to hang on and move around that way. I don't think his whole weight is supported, because that would be pretty incredible. But I think his weight is supported by the rope that has a tension force on it, counteracting gravity. But then by using the suction cups, he can move himself around and use those compression forces to keep himself attached to the glass. To the glass. I'm sorry.